My name is Jivitesh Sharma, and this is my video recording for my IBM Capstone Coursera project. Uh, I have chosen the topic of conducting a time series analysis on the COVID-19 pandemic, and my use case for this project is that hopefully we can use some machine learning and deep learning algorithms to predict the future number of daily cases or deaths and recovered uh, during this pandemic. Okay, beginning with the first cell with just a couple of imports. Let's run that first. And beginning with the dataset, I've collected this COVID-19 dataset from Kaggle. Kaggle is an open source data library which has thousands of datasets. I found this dataset on Kaggle, and it was the official uh, dataset on the number of confirmed cases, deaths on a daily basis, recovered, active cases, as well as some other stats for the virus. And this data has been verified by Johns Hopkins University and Worldometer, so it's the official dataset for COVID-19, and thus I decided to use this for my project. Yeah, beginning with data exploration, we first look at some basic info of the data, looking at the name of the columns as well as the data type. Next, moving on to see if any of the columns have any null values. Everything looks all right. And going ahead with the basic ETL processes, the first transformation I'm going to do to the data is basically replace the first cell of new cases, new deaths, and new recovered. I'm going to take values from that and set it to confirmed deaths and recovered. Why I'm doing this is because the three columns confirmed deaths and recovered do not have the value for the cases on day one, whereas new cases, new deaths, and new recovered are a cumulative sum of all the data, so they do have the value. Thus, I have just copied the data onto the first cell, so we have a full set of data for our confirmed daily cases. In this project, I'll be only looking at the confirmed daily cases, and we will be conducting and analyzing um, the number of daily cases which have been confirmed. After I have done that, I set the index of our data frame as date, which used to be a column earlier. Then I save the daily data. I save the data frame into a variable named daily data, which has the columns which we required filtered out, which only include confirmed deaths and recovered. And I convert the index from uh, um, whatever format it was to date time. Next, see if there's any null values in our daily data variable, and this is how our data frame looks like. This is the data as the index in dot to date time format, and these are the three columns out of which we'll be only focusing on the new cases. Going ahead with plotting data, I just wanted to visualize how our daily cases are looking like, what is the trend, and how basically the data maps out across all the 7 months from January till August. Next, before we go ahead to implement any of the machine learning algorithms, I would like to split the data into training, validation, and test. I'm using in this case 70% as training data, 20% as validation data, and 10% as test data. Next, looking at the shape of the data we have, as we can see, we have 131 observations for train, 38 for validation, and 19 for test. Next, moving ahead, doing some basic feature engineering and data transformation. First, I would like to scale the data. Thus, I've used a min-max scaler. The data is not normally distributed, and if it was, I would be using standard scaler. But in this case, as we saw, the data is not normally distributed through this plot. I've used min-max scaler. I've created a pipeline with the step scaler, and I fit the pipeline on my train data frame, and then use that a pipeline and transform all of the other uh, data splits I had created, validation and test data frame. Running this and visualizing how a normalized data looks like. Next, I'm creating a function which is split the data into windows which we can work with. This function is inspired by Jason Brownlee, and it basically splits the data into the specified number of steps we specify in the function argument. So it basically creates windows for data which all the models will work on. Running this and using split sequences on our data frames with a step size of 10, which means that our model will be looking at data of the past 10 days to make a future prediction. Next, I would also like to look at the shape of the data after we have split it. As you can see, everything looks perfect with the 10 representing the 10 chunks we have created of the data, the 10 windows to be exact. Next, before going on to applying any deep learning algorithms, I would like to implement a machine learning model. As you see, the relationship in the data was kind of linear and had an upward trend. I decided to use linear support vector regression. Here I am going to fit two different linear support vector regression models with different loss parameters, epsilon insensitive and squared epsilon insensitive. Squared epsilon insensitive is a regularized loss parameter when being compared to epsilon insensitive. I have done this. I have trained two of these models to see which performs better on the dataset. Next, after fitting these models, I have made the predictions of both of our regressors on X-test and plotted our predictions just to see how our model performance is. As you can see, the blue represents the diagnosed cases and the various other lines represent epsilon insensitive and squared epsilon insensitive loss respectively. Both the loss parameters perform fairly well, so we need to look at some evaluation metrics before we can choose a final answer. Here we are looking at mean absolute error, root mean squared error for both of the loss metrics. I have plotted a scatter plot with the x-axis of RMSE and y-axis of mean absolute error. As you can see, the squared epsilon loss has the lowest value for both and thus seems to be the better model out of the two. Next, I would also like to create some deep learning models which I could compare with the linear support vector regression to see if they perform better and can learn the underlying function behind the data. Before moving on to some complex models, I created a simple linear model first with loss metrics of root mean squared error, and mean absolute error. This only has one dense layer. I fit my model for 1,000 epochs. It will take a few seconds to run. Once the model is done running, I can move on to look at some of the evaluation metrics. As you can see, the model has been fit. These are some of the loss metrics. To better visualize these metrics, we can create a graph. I have created a graph of the RMSE, MSE and MAE score on the validation data which was provided and how the loss has basically been decreasing over time through the epochs. Similarly, the train and test loss through the 1,000 epochs, as well as the model performance by basically plotting how the model performs on x.test when compared with the original data, which is represented here in blue. As you can see, this model didn't perform as well as the linear support vector regression, and so I decided to move on to create a multi-step dense neural network model which has more than one hidden layer, so it would probably increase the performance on the test set. I'm only running this for 250 epochs as it takes some time. It has been a fit. Looking at some loss metrics once again, comparing the loss metrics between the train and test sets, plotting the validation metrics. As you can see that throughout the 250 epochs, our RMSE, MSE and MAE score has been decreasing, which is a good sign. Our train loss and validation loss also decreased, which is a good sign. And our model performed much better than our linear model. So this is a positive sign, but I think we have still one more deep learning framework to implement on time series, which is the LSTM. Here we have an LSTM with um, two LSTM layers and one dense layer. I have fit this model for 100 epochs as it takes time, and used the XVal and YVal validation data to validate the model. I have also looked at some loss metrics, which we will once again analyze. Okay, as you can see, looking at some of the loss metrics, we see the loss score, the RMSE score, the MSE, and the MAE score respectively. To better visualize these metrics, we can plot them and see that throughout the 100 epochs, our score has been decreasing, which is a good sign. Next, we plot the train validation loss, which has also been decreasing and is another good sign that our model is working. Finally, we create a prediction. We plot a prediction of the model against the original data. Unfortunately, the LSTM did not perform as well as the dense neural network or the linear support vector regression, maybe because it was too complex of a model for such a simple function. But before we go ahead, I would like to do a model performance comparison by plotting down the results of all the model against the actual test data. Running this, we see that the original data is in black, whereas all the different models are overlapped around it. And one of the best models we have are squared epsilon insensitive model and the predicted cases uh, by our dense model, which is in red. Moving ahead, I would like to further analyze the evaluation metrics between our dense and LSTM models, because I had been observing that our LSTM's evaluation metrics were much lower than that of our dense model. As you can see, I was wrong, as the data suggests that our dense model is performing much better than our LSTM model, with a lower root mean square error as well as lower mean absolute error. So choosing a final deep learning model is the last step of this exploratory research. But before that, I would like to explore the effects of normalization. That means that I will be implementing both the LSTM and deep learning models on the original data frame, which was not been normalized or scaled using the min-max scaler to see how they perform. Looking at the shape of the unscaled data once again, and training our unscaled model on and training our dense model on the unscaled data. Similarly, I'll train the LSTM model on our unscaled data. And we will next, after they have been trained, we will go ahead to see the evaluation metrics of each model to finally decide which model performed the best. As we have seen, it has been fit, and these are some of the evaluation metrics for our dense model, a few evaluation metrics for our LSTM model, a score of the evaluation metrics across the 250 epochs for our dense model. Similarly for our LSTM. Next, looking at the model loss of the dense model and the model loss of the LSTM model, and then finally plotting the test, uh, plotting the predictions of each of the models on the test data with the original data. As we can see that on the unnormalized or unscaled data, the dense model performs extremely well, mapping out almost the whole trend of uh, the data almost perfectly. This is the end of my exploratory research, and thank you. Hopefully, it was worthwhile, and I was able to understand a lot about these models, and um, would like to and have created a Jupyter a notebook which I will be sharing with the with the examiners and my peers as to so that they can open and look at my research and also appreciate my findings. Thank you.